We're live.
We're
All
live.
right.
Well, good evening and welcome to the Quadrivic Mathematics meeting with Daniel Jones and Chris Garcia. I'm Catherine Fratz. I represent Peak Educational Solutions and I met Daniel here recently. I work with classical schools in the Midwest region, and when I got a chance to observe Daniel and the way he approaches mathematics, I said, we have got to find a way to share this with others. So I'm here to support him. We're also here with Chris Garcia. Chris Garcia is a former student of Daniel Jones from University High School. He worked with Daniel throughout high school, and it had a huge effect on his mathematical understanding. He is now a computer programmer in Tennessee. So I will turn it over to the illustrious Daniel Jones, a passionate mathematics educator who's been educating students from University High School, Veritas, Logos, Genesis, just all across the United States. So Daniel, take it away.
Okay, thanks, Kathy. Appreciate that. And thanks for coming, everyone, tonight. So the reason we're here is, well, there's lots of reasons why we're here. So let me try to see if I can boil it down. I taught at University High School for 15 years. While I was there, I was given a lot of freedom with respect to how I teach geometry specifically. And while teaching, I was really curious myself about how mathematics works as a young teacher. And I found myself often asking my students questions to see what they thought about things. I would often pose questions like, what do we mean by a circle? Things like that. Or what are the 9 postulates that give meaning to the lines and planes of space? Those kinds of things. In that process, I developed what I now refer to as quadrivic mathematics, like Kathy mentioned. Chris Garcia was one of my students at the time. He represents, I'm not sure how large of a group, Chris. He could probably speak to that. A group of students that really had a lot of takeaways from what we did in class at University High School, which I'll refer to as debate style mathematics, which we're not going to talk much about tonight. But debate style mathematics is a way of instructing mathematics to get the kids as involved as they possibly can. So as time allows, we'll talk about what that is. I've been bouncing around a little bit since University High School. I've now landed myself at Genesis Academy, here closer to my roots, in Mapleton, Minnesota. I teach in Winnebago, Minnesota at Genesis. And I have the blessing, I have so much support from the administration here at Genesis, and I am just having so much fun continuing to do what I do. And so the reason, like Kathy mentioned, the reason we're doing these recordings is because we want to share about quadrivic mathematics. And so these evenings that we're doing here in these Zoom calls are devoted to we call them the books of arithmetic and geometry. Quadrivic mathematics essentially maintains the premise that mathematics should be taught according to a clear distinction between arithmetic and geometry, which is not how it's been done since the 19th century. Modern mathematics does not make that distinction, as I think you will see if you stick around for these talks, or I guess these discussions. And so what we want to do is walk you guys through the content of what quadrivic mathematics looks like almost like a roadmap of what quadrivic mathematics is. What is quadrivic mathematics, and how can we use quadrivic mathematics to better understand the world around us, frankly, from a mathematical standpoint, and to be very extremely classical in our approach to understanding mathematics. That's my introduction. There's a lot more to say, of course, but we'll get into that as we go. I'm going to hand it over to Chris. Chris, if you could share just maybe your experience and why you think this is important.
Yeah. So obviously, taking Jones's class had a pretty big impact on me. I'm still here like a decade later. I think that was twofold. I think in part it was the content itself, its approach, and I think the other part was the way that it was actually taught. Um, like Jones mentioned, we're not going to be able to get too much into like the actual open debate style. That's something that really just has to be experienced, I think, or at least observed in person to kind of start wrapping your head around. But it does lend itself very strongly to, I think, this type of material. It's very empowering. I really like the way, I think it was the way you put it, Jones, or somebody here. It really helps you feel like you have ownership of the content, of the concepts, of your own understanding. Doesn't feel like you've been force fed it. It feels like you've grown the tree and you've taken a bite of that apple, so to speak. Um, but yeah, speaking more to the content and what makes it special, it's something that can be very difficult to articulate. But I think if I can take a stab at it, what makes this approach to mathematics so powerful is its simplicity and how natural it is. There are a lot of things that we take for granted as human beings that are living in a physical space. Um, there's things that we take for granted as people who speak language. There are just certain things, if you've ever like come into and try to like articulate an axiom, you know exactly what I'm talking about. It is so difficult to put into words things that you do without realizing you do them. Um, and so, one of the most fundamental things I think for people is how we come to the knowledge of and understanding of relationships and how things relate to one another. As toddlers, right? As we first start forming our first words, that is us making our very first associations of associating a sound with a physical object, which as we mature and grow becomes more than just the singular object, but rather its identity or its conceptual, right? Like the Platonic chair type example, right? Like you grow up and you start to associate the sound of chair with what a chair is, the essence of a chair. And this is something that's really it's more of a psychology thing, it's more of a language thing, but it is something that is common to all people who are living in a physical world. It's how it's an audible and a visual in terms of like writing representation of what happens mentally for us with these associations and these relationships. And so I think what's so cool about the way we're approaching mathematics in this way is that the construction of mathematics is built in the same way, using the same tool set as the way like language is constructed, which is like second nature to us as human beings. um, I think language is very much a part of like the human experience. And so that makes this form of mathematics a lot more natural, a lot more simple, and a lot more grounded. And not only that, by exploring mathematics in this way, it helps you kind of get like a bigger picture on now that you have mathematics as a system built in the same way that you kind of build language. It just kind of on a personal level helps you kind of better understand like how it is that you're even interacting with the world around you. You become a little bit more aware of the way that you navigate the world and the way that you think about things and come to understand things, which in turn can be very helpful in all aspects of life in more effectively and efficiently coming to understand and grasp other types of concepts. So it's simple, it's elegant, it's natural, and its applications go much further than the mathematics itself. Um, so that's my stat. That's my long-winded, somewhat rambly stab at what exactly is the sauce here. What's in the sauce? How do you make it? Yeah. Any thoughts on that? Questions? Feedback?
Kathy, do you want me to go ahead and run the whole thing, or do you want to keep leading us through? What do you think?
No, I'm going to turn it over to you, Daniel.
Turn it over to me. Okay.
I'm turning it over to you, teacher.
Okay,
Before you
that's
jump in
go
really
for it, Bill. Yeah.
quickly, so just to clarify, especially for people who maybe weren't here before,
Yeah.
um, w- this is obviously a big project, a big goal. Um, where do you envision it beginning? Because while we start to acquire language from the very early age. We even learn to read down when we're 4, 5, 6 years old. This program that you're talking about isn't aimed to be simultaneous with that language acquisition. It follows the same process or method perhaps, but it doesn't happen at the same stage of development or maturity. So when do you introduce this math that you're talking about? And it must not assume any prior experience with math because, and you can answer that, but I mean, assuming that this isn't a kindergarten book, uh, our students who are going to go through this math will have had previous encounters with mathematics or with with numbers. I mean, this is part of our definitions that we need to handle, I know. But so can you just position it really quickly
Yes.
for where are we talking here?
Yeah, great question, Bill. So I could answer that question in many different ways, but where it sits right now in my mind, and as far as where it's been functionally in places I've taught, what we're studying today is the beginning of seventh grade mathematics. Seventh grade mathematics. The students will have already had much exposure to numbers, sixth grade math, fifth grade math, all the basic things like greatest common factors, those kinds of things, maybe a little bit of algebra, that kind of thing. But yeah, like you said, this is designed to be the very beginning. Kind of like, the beginning is a very good place to start, kind of thing. So we start with definitions that, exactly like Chris said, starts with forcing or bridging language and mathematics immediately with the first definition, so that everything that's studied in mathematics can be well defined in sentences, assuming that a person knows how to make a sentence, right? Starts with sentences, goes into logic right away, truth tables, that kind of thing. We're assuming that truth tables are actually, because we talked about this last time we met also, logic hopefully will have been at least studied informally before this, so students can like think about things logically, but really it starts with the idea of sentences and a student knowing that a sentence in this context has to be either true or false. And you just kind of branch from there. Great question, Bill. Thank you. Good. Chris, you want to add to that at all?
I think that covers it pretty well. I mean, you kind of get the similar, like, I like the distinction between kind of like the informal background knowledge and then really diving into it. That was kind of my own experience getting into like junior year of high school, taking like AP language and like learning all this stuff about like how much you can really play around with like language itself and how much of the brain is dedicated to it and those sorts of things. It's like, yeah, I've been making words since I was a toddler, but I didn't realize there was so much more going on under the surface kind of thing.
Yeah. Yeah. So, like Chris said, we're looking at things under the surface. And I teach this to my seventh graders, and it goes really well. Even for the ones that aren't ready for it, it kind of puts them in a situation where they have to get ready for it really fast. Let's dive in, I think. I'm going to try to keep this an hour if we can. What I want to do is have someone read the definitions, and as a person's reading, Chris is drawing and expounding on as we go, and I'll just kind of fill in with color commentating as we go. That's how I teach anyway. I'm not comfortable being the lead man. That's just not how I roll. So I'll kind of fill things in as we go.
I'm happy to read.
Perfect. Read my mind, Dale. Okay, so Dale's going to read. Chris, stay on the same page with Dale, right? Let him know if he needs to go faster, slower, that kind of thing. I'm going to listen and speak as necessary. Otherwise, I'm going to let Chris and Dale kind of take the show.
Let the following be defined. First, a predicate is that which can be said of a thing. If that which is said of a thing is true, then the thing is said to be a subject of the predicate, and the predicate is thus said to be predicated of that thing.
That was a lot of work. Let me say something. One thing Kathy mentioned to me, she wanted to make sure I do, is that this book is devoted to set theory. This first book is devoted to set theory. Set theory, from a mathematician's standpoint, is the foundation for all of mathematics. From my standpoint, it's the bridge between humanities and mathematics. And I think it's actually both. So a predicate is that which can be said of a thing.
Yes. My backup of my prepared notes is a flat file, so I'll have to recreate on the fly. So we've got what can be said of the thing and the thing. So this is just like a very, very basic example.
So as Chris is drawing there, the predicate is that which can be said of that thing. So in this case, the predicate is blue. It's in quotations right there in the middle, is blue. Is blue can be said of that object because the object is blue. So basic, right? Anytime you make any sentence, you're actually already invoking mathematics. If I say this is a pencil, right? Is a pencil can be said of this thing. Any sentence you can make, especially a simple sentence, right, has a subject and a predicate.
Yeah. So very, very fundamental. This is that bridge between language and getting into building mathematical systems.
Kathy, do you have any questions on that right off the bat?
Letting this be the second time around, I'm hearing it differently. So for what that's worth, for anybody who's watching this the first time, the second time around, it starts to sink in a little better.
Can you tell us how you're hearing it differently?
Well, as I mentioned, as a humanities person, I would see the word subject and predicate, and I'm going to put them in that framework or that understanding of what that term means to me in grammar. And so I needed to look at it a little differently, and I'm still probably processing because I can't those definitions still need to exist, as well as what I'm trying to understand with the quadrivic mathematics. So as I reconcile those differences in my mind, that's where it's starting to feel more at ease, the reconciliation.
Okay, Dale, can you read the definition again, maybe a little bit slower? Let's just make sure everybody hears it one more time, because the part that he read about if that which is said of a thing is true is really important also from a mathematician standpoint. Go ahead.
First, a predicate is that which can be said of a thing. If that which is said of a thing is true, then the thing is said to be a subject of the predicate, and the predicate is thus said to be predicated of that thing.
So is blue is predicated of the sky because it's true. If it's true. If I say the sky is green, since that's not true, we wouldn't say is green is predicated of the sky because it's not a true statement. So that immediately forces logic into the system because we're invoking truthfulness, assuming the students already know what that means. Like they have to have some previous understanding of what logic and what truth is. And on a human level, you can get away with that, the intuitiveness of that, but formally, it's dependent upon the statement being true. That's what makes it a subject. And mathematically speaking, that's huge because, there's several proofs where A is either an element of B or it is not. And that comes from the law of, what's it called? The law of non-middle something. Bill, help me out with that one. The law of
non-contradiction.
Non-contradiction.
The law of excluded middle.
Oh, the excluded middle.
Yeah. That either A is an element of B or A is not an element of B because a statement is either true or false. If it's true, it's an element of. If it's false, it's not. So that's where the subject and predicate. I jumped ahead a little bit because element's next definition, but that's what we're getting at with the subject and predicate relationship. It's whether or not it's true or false, the statement that you just made. Kathy, does that make sense?
Yes.
So
Okay.
if I just really quickly, and I know we don't have time to go down this road, but if I'm a thoughtful student in your class and I select this time to say, but not during sunset. So the sky is not blue during a sunset. So
Yeah.
does that make this not work?
Whew.
Or is that where you get into the debate part?
That is part of the debate, but I would just turn back that back to the students, see what you guys think. And if the students say, well, the sky isn't blue, then I say, then it's not true. So it's not a subject. But it is. I said, then it is. And let them decide whether or not it is or not. Just put it back on them. That's how I usually handle those kinds of things.
Okay.
Let them decide, is it or is it not true?
So you'll get to other qualifiers later, but the fundamental principle here is if we can accept this as true, then we can move on.
Exactly. Exactly. Which is why debate style has a lot of consensus building, right? The idea of consensus is built into debate. You debate until there's a consensus. That way, if we agree something is true, you don't go back. That's like something you establish to be true, and then you build on that later. It's like a system that's built upon consensus building through debate. That's what debate style is. Right, Chris?
Yeah. Yeah, we'll get into that a little bit too, I feel like, with sameness just a little further down.
We ready for that? Second, two things are said to be the same if each is a subject of every predicate that the other is also a subject of. Two things that are not the same are said to be different.
All right, Chris, can I explain this one while you're drawing?
Yes.
Two things are said to be the same if each is a subject of every predicate the other is also a subject of. That's a very difficult concept for seventh graders to wrap their minds around, but with some examples, they start to get it. Okay. So for example, are these two items the same? You guys can see them. There's a red pen and a black pen. Are they the same? Obviously, we could say they're the same in some ways, right? But strictly speaking, what this definition is trying to get at is that these two things aren't the same. In mathematics, with the foundation of mathematics, you have to have some level of definition of sameness that's required in mathematics, along with the axiom of extensionality. Okay, and that we're going to get to those things in a very informal way in these books. So these two things aren't the same object. That's what we're getting at when we say that they're the same. They're the same exact same object, identity. So in other words, this red pen and the pen I'm holding in my right hand, I've just described it two different ways. Those two objects are the same. They're one and the same. That's what we're getting at because each is a subject of every predicate that the other is also a subject of. Okay? Which means that anything that can be said of this pen can also be said of the object in my right hand. Right? If I think of something that can be said of this red pen, it's red. What else can be said of it? What can be said of the object in my right hand? Red, it is red can also be said of that, right? So if it's the case that every statement you can make about this pen can also be made about the object in my hand, then the two things are the same. And the reason that that's necessary is because that is the essence of what we call the substitution property in mathematics, which students don't know where that comes from. Why can you substitute one thing for another if they equal? It's because of this definition of sameness, that whatever can be said of one can be said of the other. Therefore, if x plus 5 equals whatever, right, and we know that x equals 7, we can plug in 7 for x because x and y are the same. Everything that can be said of one can also be said of the other. It's the substitution property at the foundational level. I feel like I'm talking
So
a lot,
Daniel,
yeah.
are 2 plus 2 and 4 the same?
2 plus 2 and 4 are the same, yes. Everything that can be said of one can be said of the other.
I agree. That's great. We ready for the next one?
I'll just point out here, I mean, this is probably nothing novel to you guys, your mathematicians and teachers, but just the chaining of definitions, the building, the construction of the system. From my perspective, as like a sophomore in high school taking this class for the first time, this was like kind of one of the first classes where I felt like I really properly saw an actual system unfold and build before me. I honestly don't know if I've taken a class since that really built on it that way. And so it's something that to keep an eye on. You get some really cool interactions later on. You kind of see like almost sort of fractals with the dynamics between the building and the chaining of these definitions. It's really hard to see in the early stages, but you'll start to see a glimpse of it once we start heading into book two, particularly when we start getting into like I think multitudes. You'll start to see this kind of like pattern emerge that kind of starts to reverberate and get bigger and bigger and bigger, which it's kind of like the small dominoes at the beginning, eventually being able to topple like the Empire State Building, which back in the day was like
Chris,
real numbers.
This?
Yeah, so
Would you
they're
explain
chaining
this
here.
diagram to the group?
Yeah. Okay. So we're building here, right? We've got two things that said to be the same. If each of the two things is a subject, right? And so remember before our subject was on the right here. Our subject was the thing. It's the subject of something if it's true of its predicate, right? So these two things, are said to be the same if they're subjects of every predicate that the other is also a subject of. And so our previous definition necessitates that if these things are subjects of a number of predicates, then those number of predicates can be said of those things truthfully. And so we work out to this diagram where, for the pen to be the same as the object in Jones's hand has to mean that everything that can be said of either one of the two is true for either one of the two.
And that makes them the same by definition.
Yeah.
So one can be substitute for the other in any sentence, which is what we're trying to get at. Yep.
Yeah. And then this was one of the examples I pulled straight from the old doc. Same in color, but different in shape. So to a degree, it depends on what you're willing to ignore.
Yes.
Because you can always make the argument that two things are not the same if you want to get nitpicky enough. You can say that they're not the same purely because you talked about them at different moments in time, if you really want to. But at some point, right, you got to settle on some level of detail. Going back to the sky earlier, you can make the argument that the sky doesn't really have any color. It's just air. Like the color you see is just like refracted. Is that really the color? You can get lost in the weeds with that. But yeah, it's a spectrum.
So you aren't ignoring reality, but you are describing reality and you are choosing the limits of your description.
Yes, exactly.
Yeah.
Which is the best we can do with our language, right? Yep.
Yeah. That's all I have for the second one.
Third, the extension of a predicate is that which satisfies the following axioms. 1, every predicate has an extension. 2, all the extensions of any given predicate are the same.
Does anybody understand what that's saying? Dale, you want to try? What is that saying to you?
I don't want to try.
Okay, okay. Bill?
Boy, I don't know.
Let me read it again. The extension of a predicate is that which satisfies the following axioms. 1, every predicate has an extension. So the example Chris has there is being blue is the extension of the predicate is blue. Now, you can't actually define I still think, Kathy, it's called a gerund or a verbal noun. In this case, being blue is the extension of is blue. And mathematicians have all agreed they do not know what a set is. What the heck is a set? They want to say it's a group of objects, but what's a group? It's like a collection. What's a collection? It's like a set. That's just replacing one thing with another, right? And as all mathematicians know, the only way you can stop that vicious cycle is by introducing axioms. Once you can't define something because you're such a low level, you now have to describe how it behaves or describe it somehow with postulates or axioms. So what we're saying is that even though we don't know exactly what a set is, okay, and I think of a set as a gerund or a verbal noun, like being blue, because it works so well with all the examples that we have. So I would say that a set, by the way, the reason I'm using the word set is because later we're going to define a set as the extension of a predicate. So we're trying to get at the basis of what a set is. We don't know exactly what it is. We just know it has these properties, and that is as far down as you can get. This is the basis for all of mathematics. That's why we can't define it. It's the very bottom. So a set, or the extension of a predicate, is that which satisfies the following axioms. And as long as it satisfies this, fine, that's a set. That's good enough for me. Number one, every predicate has an extension. So is blue's extension is being blue. Okay? The reason I'm using that example is because that's the axioms in the entire framework is going to force us to think of any gerund as a set, which is what we all already do naturally when we think about sets. This is just us articulating what we already do. And my claim is that this is the correct or truest articulation of what we actually mean when we say a set or a group or a collection. What exactly is a collection? I don't know how to define it. It's this. It's that which satisfies these axioms. Every predicate has an extension, right? If you say the sky is blue, you're already thinking about everything that's blue. You're already thinking about a set. And that set that you're thinking about is the extension of the predicate is blue. Kathy, does that make sense?
So I'm translating. I can't help it. I'm translating. I'm like, okay, so now you're talking about a being verb, right? You am is are, was is were, has have, like those are, you've got the logical connection is blue, and then being blue. It's still in the same group of words in the being verb.
Yeah. So the reason being blue, I'm going to write down on paper for myself.
Yeah.
I'm going to write down being blue. The reason that that is a noun is because I can say being blue is great. Being blue, the noun, is great. Now suddenly being blue becomes the subject of another predicate. If being blue is great, if that's true, then being blue becomes the subject and is great is the predicate. Because in mathematics, that happens a lot, Kathy, where suddenly our sets become the elements of other sets.
Okay.
A lot. It happens so much that mathematicians are like, okay, how do we deal with this? And they have some weird ways of dealing with it. And some of them say like, okay, just everything's a set. But I don't think like that works as far as ontologically correctness. That's actually the most popular theory right now is that just everything's a set and we just don't care what they are. They're just all sets. We don't know what sets are, just everything's a set, and then we can make these relationships. Actually, that's not how the real world is. Yes, I can see myself as a set of cells, but I'm not thinking of myself as a set of cells when I say Daniel is the teacher. Daniel is the subject, is the teacher, is the predicate. But if I want to make being a teacher into a noun, suddenly that becomes the subject of being a teacher is fun. So is fun can be said of being a teacher. So that becomes a verbal noun. Being blue is a verbal noun.
What other examples of things can you give that aren't sets?
Good question. So a magazine is not a set. Of course, if you're looking at it a certain way, you can think of it as a set of pages. I get that. But if you're thinking of it as just the magazine, where you have magazines, those become, I think they're called R elements in modern set theory. R elements are like the base level things. So anything that's not a gerund, Dale, would be a thing. Anything that's not a gerund would be a subject that's not a set. Yeah, there you go. So anything that is a set has to be a gerund. Go ahead.
I'll point out that this is almost the exact same dynamic that we have with sameness, right? It's the degree of detail that you are choosing to have within your specific window of context. That is the only thing that differentiates being Daniel from being a collection of cells.
Yeah, absolutely.
Where do you want to stop diving into it?
Does that answer your question, Dale?
Yes, it does. That's great.
But being this magazine could be a set.
Oh, that's a good question. Being this magazine? Yeah, that'd be a monad. That would be a monad.
Okay.
Dale, you recognize it as a singleton, right?
I don't use either word very frequently.
So yeah, and so we'll get to this later, but I've chosen different languages to represent different things because we need all the different languages because there's so many things to describe in mathematics. So monad, dyad, triad, tetrad, right? Those are all Greek. Yeah. And those are actually well established in our history, so it works really well. So being this magazine, Bill, good example. That would be an example of a monad.
We ready for 4?
Let's see. This extension.
Yeah.
Yeah.
Fourth, A set is the extension of some predicate. The subjects of a predicate are said to be the elements of the set formed by it, and the set is thus said to describe its elements.
I
3.
spent, hold on, stop
Oh,
right there. So I spent, forgive me for all this commentating. I spent so much time trying to find the right word. Modern mathematics will say a set contains its elements. The reason I choose the word describe is because once you settle on a set being a gerund, in real life, gerunds really do describe their elements. Being blue describes the sky. So we're suddenly still in the realm of language. Now, Kathy's over there trying to catch up, probably, because what Dale just read, every mathematician knows this is like so common to us, it's like second nature, right? Dale, read it again for Kathy's sake.
4th, a set is the extension of some predicate. The subjects of a predicate are said to be the elements of the set formed by it, and the set is thus said to
Stop there.
describe
Stop
its
there.
elements.
So, so the elusive set, Kathy, that mathematicians just have a hard time defining, we've just defined. It's the extension of some predicate. So if I say set A, I know it's the extension of some predicate, that kind of a thing. So a set is the extension of some predicate. And if, let's say, if the statement is true, then the subject is said to be an element of the set. So since the sky is a subject of is blue, the sky is therefore an element of being blue. Subtle difference, but it's necessary to bridge, to bridge with modern mathematics, because modern mathematics talks about sets and elements all day. Kathy, talk to me.
Hold on, I'm still processing. Because, so our subject's elements.
You want to take that one? Our subject's elements. So I'll answer it. It's a relationship. So the pen, its relationship to is a pen is a subject relationship. But its relationship to being a pen is an element relationship. So this is a subject of a predicate, but therefore it's an element of a set. So it's a subject and a predicate. Just like, am I a husband or am I a father, Kathy? Am I a husband or am I a father?
Yes.
I'm a husband to my wife. I'm a father to my children. The pen is a subject to the predicate. It's an element to the set.
Okay.
Daniel, what what predicate is the set of the pen in your hand and the glass in my hand, the extension of?
Like
Things that
the
I just said
Is
in
a
my
thing.
in that sentence. Okay, okay.
Sure. Yeah.
I'm talking
Yeah.
about
Things you just said in the
the
sentence.
I'm talking about the set that only contains the pen in your hand and the glass in my hand. What predicate is
Thank
that
you.
set the extension of?
Yes. Yes, Dale. That is excellent. In fact, Bertrand Russell addresses that exact question in his introduction to mathematical philosophy. He said, how do we describe exactly like you said, two things that seem to be unrelated? You got to be creative and come up with a predicate and say like, is that or something like that. Does that answer your question? Or you could say the two is one of the things I just referred to. Is another way you
is
could
a
say it.
Sure.
pen in Daniel Jones' hand and is a glass in Dale's hand.
That's another way to do it.
And then the extension set would be being a pen in Daniel Jones's hand.
And
And
yeah, and to just so people understand where Dale's coming from, right? Dale's a mathematician, so he's thinking like, okay, in modern math, we don't think of sets this way. We don't have to necessarily find a predicate to give meaning to a set. We just draw a circle around them and call them a set. So if I may speak for you, Dale, let me know if I'm not correct. What he's thinking is like, okay, if that's how sets are in the mathematical world, and now Jones is coming along and redefining what a set is, how do I make that bridge seamless so that the mathematician who's used to seeing a set as a collection of things and not as a gerund can reformulate their understanding of a set on a new foundation so that they can still think of a set as the same thing that they already knew what a set was with a different definition by constructing these sets through predicates. Am I correct, Dale?
Yeah, that is where I was coming from. And uh it makes those sets that are kind of invented for examples seem cheap because yes, they can be defined as extensions of some predicate, but it's almost like repeating the sentence that you use to define them.
Yeah. Yeah. Very cheap. Very cheap, but it works. And actually, I think this actually is how we do things in the real world anyway, because there's really no association between those two things, except for the fact that you mentioned them both. So the cheapness is actually very accurate.
They've
I
never been
mean,
put in a set before.
yeah,
Well, that's
there
debatable.
are there are maybe like some nicer ways to put it, like the objects being held by two of the male participants on this call. Some a way you would actually think about it a little more naturally. And then the set
Yeah.
that contains them would just be being those things
That
that
And
are
just
being
points
held.
out to that just means I'm not creative in coming up with examples.
yeah, the onus is now back on the student. And to be frank, us mathematicians are enjoying this conversation, right? So I'm going to get back to the main point for Kathy's sake, right? The main point, Kathy, is that math can be described linguistically, and we've just shown how. Because if set theory is the foundation for mathematics, and we just defined what a set is purely in linguistic terms, there's now a bridge between the two. Does that make sense, Kathy?
To a degree. I couldn't follow all the, I mean, I could kind of follow a little bit, but just not completely. Um,
I mean, I know how Dale works, right? Him and I are mathematicians. We could
Yeah.
go on and on about all kinds of applications.
Well, maybe for Kathy's sake, and this might take us too far afield, but
That's okay.
can
Go for
you
it.
can you briefly say, because we would say that use of language in mathematics is unavoidable. So if we're going to talk about math at all, we're going to use language. So how is this approach through language different than modern mathematics, which we could talk about, but would not be the same,
That's all
even though
you're
we're
gonna.
using words for both?
Okay, this is exactly what I was trying to get at the beginning of the call, right? So what we are doing right here is we are creating in our mathematical system that we're forming these associations, the creation of these sets based off a descriptor, which is precisely what we do as humans with language for the associations or the sets that we form mentally with things. It's the exact same thing. We already all do it without realizing we do it. We are just codifying how to do it for math.
Yeah,
And we're just choosing some specific words, some specific verbiage, literally just to make it easier to talk about. But the concept and the framework is exactly the same that we use as humans when we speak words.
so yeah, and just to jump in, so Bill, it's not different. That's the point. That's what Chris is trying to say, is is how math is, but no one's articulating it. This is an articulation of what we actually do. That's
So
why
And
that's why it's so real.
we're trying to get underneath what modern math takes for granted by calling attention to the very thing we're doing and not just assuming it.
Exactly.
yeah,
It's
How much time do you think should be spent on like I think it's important to call our attention to the assumptions that modern mathematics makes. But at some point we need to move on from acknowledging those differences to for lack of a better verb, doing modern mathematics. We need to get on to solving quadratic equations and defining derivatives. I'm not sure if I'm making sense. Like I love this foundational discussion that we're having, and I agree with it. I'm wondering how it goes from foundations to trigonometry.
and that's why we're here. That's exactly what we're gonna walk you guys through. I mean, your question is about time. Like when at one point do you move on? I mean, the purpose of this is to show you the connections. Obviously, every teacher has to make that decision. Do I want to spend all my time just on the first book because it's the foundation for all mathematics? I don't think you should, but a person could do that, right? But at least the teacher has access to, through quadrivic mathematics, what these things are, so they can decide, are their students even ready for this? Right? It's not so much dictating this is how you teach. It's more giving the teachers the tool by which they can teach more effectively to whatever degree and whatever depth they choose. Chris, would you agree with that?
I would agree with that 100%.
Does that answer your question, Dale?
Yes.
Kathy, any thoughts? Just keep on rolling.
Yep, let's keep rolling.
All right.
Okay.
Fifth, if every element of one set is also that of another, then the first is said to be a subset of the second, and the second is thus said to subsume the first.
Okay. I've got a pretty good drawing for this. Well, I say it's pretty good. Like it's not the most basic, set theory, circles and dots drawing. This is what we're getting after.
Yeah, talk to us, Chris.
Okay. So, all right. So if every element of one set, so our one set in this sentence is being a triangle, right? So if every element of one set that is being a triangle is also an element of another set, which in this example is being a polygon, then the first is the first set being a triangle, is said to be a subset of the second set being a polygon. So what this tells us is being a triangle is a subset of being a polygon because all the elements of being a triangle are also elements of the set being a polygon. Every triangle is a polygon. And so the set of being a triangle is a subset of the set being a polygon. And then also the second is thus said to subsume the first. So being a polygon subsumes being a triangle.
Please note, the mathematician will appreciate this because subsets, as Dale knows, are very frequent in mathematics, very frequent. And the layman who's not a mathematician will also appreciate this because these are Venn diagrams used in every field of study. The language might be a little different, right? You just say something like, every triangle is a polygon. But when you say every triangle is a polygon, a mathematician would say, therefore, being a triangle is a subset of being a polygon. That was the original idea and therefore power of set theory when it was invented, that they finally found a way to put our natural language into a mathematical way of saying it, so we can make more powerful statements with language of set theory through subsets and that kind of thing. So this isn't like hugely revelational, right? It's just again making that bridge. And this wasn't my idea, right? This is Georg Cantor's idea. He's the one that invented set theory for that purpose of bridging mathematics and language more effectively so we could solve problems that we could not solve until this was invented in the 19th century, which is very recent.
So, Daniel, in the interest of time, and just completely throw this idea out if it's not where you want to go, but looking at the definitions coming up like union, junction, intersect, difference, complement, those are all awesome and great. I am most curious about the last definition of universal, but maybe instead of jumping there, you'd rather go slowly through the definition 6 through 10.
I think so. Because that last definition, universal, I think there's a lot of debate that could surround around it. If you're willing, Dale, maybe that's something you and I can talk about after the recording. If you really want to talk about doing this recording, we can, but I do think we should go through all of them.
Sure.
Is that fair?
Yep.
Yeah, because I know exactly why you're interested in that, because it could lead to contradictions. But I don't want to talk about that necessarily right now, even though it needs to be addressed. Okay.
Sure.
Good. Kathy, any thoughts?
6.
Nope, good.
Keep on going. Okay.
6, the union of two sets is the set that describes the elements in either.
Okay. So we have the example from before where the union of being a triangle and being green is being a triangle or being green. And I think I've got a drawing here. So this sentence right here describes everything encapsulated in both circles.
Is that clear to everybody? The union is the set that describes the elements in either one. It's an or statement, not an and statement. So it goes back to logic again. This is built upon logic. Sentential logic specifically. Clear enough? Should we keep going? Okay.
7th, the junction of two sets is the set that describes the elements in both.
So junction of being a triangle and being green is being a triangle and being green. So in this case, it's the overlap here is what represents the junction.
Yeah, it has to be both to be in the junction. Oh, and a quick side note, again, for Dale and other mathematicians who might be watching this, obviously this is a break from set theory tradition, which would describe that middle section as the intersection of the two sets. The reason I chose the word junction is because I realized that geometry preceded set theory. And in geometry, the intersection of two sets are the elements, not the sets themselves. So for example, two lines will intersect at a point. The point is the intersection, the point of intersection of the two sets, the two lines. Lines become sets, by the way, in this system. Lines become sets of points. And so you have the junction of two sets contains one point because the point is the intersection of the two sets. That's why I chose the word junction as opposed to intersection to represent the set, not the elements.
8th, two sets are said to intersect if they have a common element, and the common element is thus said to join them.
So right here, the two sets being a triangle, being a pentagon, they don't intersect because no triangle is a pentagon and no pentagon is a triangle. And so let me pull my diagram over for that. So right here, the junction is empty.
Therefore, they don't intersect.
Yep. 9th, the difference of two sets, a first and a second, is the set that describes the elements of the first, but not those of the second.
So the difference of being a triangle and being green is being a triangle that is not green. I'm not sure that I have a diagram for this one, but
10th, the complement of one set with respect to another is the set that describes the elements of the second, but not those of the first.
so the complement of being a triangle with respect to being red is being a red thing that is not a triangle. So I have here for us. So it's right here, this spot.
Again, not rocket science, but it echoes our own intuition about how we see the world around us. Like all these constructs we use in our natural language all the time. And this is the brilliance of set theory from Georg Cantor, is he gave us the language by which we can infuse this natural way of thinking into mathematics I just think mathematicians walked away from that to some degree, and I'm trying to bring it back rooted in language. So I'm really not doing anything new. I'm just trying to bring us back to that joining that Georg Cantor was trying to do for us in the 19th century.
And we got there. 11, a set is said to be universal if it describes everything.
I didn't have a picture for this one. It would have been too big, guys.
So yeah, I'm gonna
Fair
jump in with
enough.
this one, Dale. So the example I have in my other, like the book that he's drawing some of these drawings from, like the shapes and stuff. An example of a set that's universal would be being a thing. That describes everything. Even the word everything, right, is described by, it describes everything. Being a
Is
thing.
there more than one universal set?
There is not. You can prove that. That's a good question. You can prove that there's only one universal set, but Dale, let me tell you right now, we haven't defined the number one yet. That shows up in book 3. So the whole idea of uniqueness, you'd have to say like any two universal sets are the same. That's what we'd be saying at this point. Any two universal sets are the same, which essentially is saying that there is one universal set, which we'll define soon.
And I love the 12th definition. And 12th, a set is said to be empty if it describes nothing. The reason why I love it is because that word undefined comes up so much in mathematics. And I like to say that the best thing that you can say about something that's undefined, like 1 divided by 0, is
Describes nothing, right?
that you could just stop talking. Yeah, there's no description.
There's the outside the box man I love right there. I love that. Yes. So yeah, so the example I always give my kids is an elephant that can fly, right? Being an elephant that can fly. Unless you accept Dumbo, etc., I get that, right? But being an elephant that can fly, like if you accept that literally, whatever that means by accepting it, right? That would be an example of an empty set because being an elephant that can fly describes nothing except for Dumbo.
Well, Daniel, I'm gonna have to get going pretty soon, and so I don't want to rush. But if there's ways that you or Kathy wants to close things out,
I think we're done, unless Chris, you want to expound on that at all, or we could close after you go. Either way.
okay.
Kathy, do you want to sub anything up for us, or should I mean I think this kind of concludes everything. Kathy, what do you think?
Yes, I was going to say, I think this is an excellent example of book the first and a great introduction to quadratic mathematics. So thank you very much, Daniel and Chris.
Could I just say one thing really quick though while you're clapping?
Please.
Food for thought for the future is that we live in a world that loves to separate fact and fiction and does not know how to handle, for example, fairy tales that can be true in one sense and not true in another sense. So even your empty set here being an elephant that can fly is an invitation to a poetic understanding of the world that may defy mathematics, but can exist in a real space in which true things are said of it. So you mentioned literal. There may not literally be in reality an elephant that can fly, but the fact that we can all say, excluding Dumbo, or that we could have our students write a story which involves something that would otherwise be a part of an empty set must speak to something a great deal more profound than either language or mathematics can contain.
You can see how philosophically deep this can get right away. And that kind of speaks to what Chris is saying at the beginning, is that suddenly math gets put back where it should be, right, in the realm of philosophy.
In the humanities.
At the same time, describing the constructs that we need to do actual mathematics, which I love.
Great stuff.
It's a wonderful bridge between the two, and we're just getting started. Okay, thanks so much, guys. I appreciate your time. Chris,
Thank
do you want
you.
to close us off? Anything else you want to say?
I mean, stick around. You're really going to see how this blossoms. I can't wait for us to get into book the second, book the third, start getting at numbers. I love the arithmetic approach. You'll enjoy what you see.
Thanks so much. Kathy, thanks for hosting tonight.
You bet. Happy to do it.
Thanks for doing this.
Yep.
Take care, guys.
Thanks all.